And also I need to share my screen. All right, so only one person here today. All right, so basically we're going to start with chapter 6, which deals with the area of thermochemistry. And thermochemistry is basically that area, of course, as the name suggests, which deals with energy changes in chemical reactions. All right. So before we actually get to that discussion about the relationship between reactions and energy changes, we need to define some terms with respect to energy and related topics. So basically, energy by definition is the capacity to do work. And work is basically what happens when you apply force to an object and the object moves. So if I were to move this bottle by applying force like this or pulling, because force can be a push or a pull, and if the object moves, then we say that work is done on the object. All right? So that's what energy is. Energy is the capacity to cause a displacement by the application of a force on an object. So if in terms of the original literal meaning of energy, it means work within, but in practice, an object cannot contain work. Now, all energy can fall into two categories. You have potential energy and kinetic energy, and their definitions are shown. Potential energy is the energy an object has by virtue of its position or composition, and kinetic energy is the energy an object has by virtue of its motion. And the formula for calculating energy is shown there, and this is specifically for kinetic energy, right? M is the mass and V is the velocity. And if the mass is in kilograms and the velocity is in meters per second, then the units of energy will be, as shown here, kilograms times meter squared over second squared, right? Or joules, right? So the joule unit is the same thing as a combination of kilogram meter squared over second squared, all right? So that would be the metric unit of energy. Now, some other terms that I need to introduce to you. I talked about what thermochemistry is about. It's talking about, or it's a discipline which deals with energy changes occurring when a chemical reaction is taking place. And when it comes to thermochemistry and also thermodynamics, I don't know if you have to do general chemistry too, but general chemistry too, there's a whole chapter dealing with thermodynamics, which delves deeper into some of the things that we're going to talk about here. Excuse me, it's very important that you understand what we mean by the term system, which, as you see there, is a part of the universe being studied, and then the surroundings, which would be the rest of the universe. So basically, we can say that system plus surroundings is equal to the universe, right? So the system could be literally anything which is a part of the universe. It could be, for example, a test tube reaction or a reaction taking place in a beaker, you know, or whatever, reaction taking place in a vessel. And we're speaking in the context of chemistry here. That's a system, right? And therefore, you know, very often we're concerned about in thermochemistry the type of energy changes and corresponding temperature changes that will occur in a system while a reaction is taking place. Okay, now as far as systems go, there are three types of systems. You have what is called the open system, where you can have energy and matter be exchanged between the system and the surroundings. Then you have the closed system, where energy can be exchanged between the system and surroundings, but matter cannot. And then the final type of system is isolated, where there's neither exchange of energy or matter between the system and the surroundings, right? So those are the three main types of systems that we will deal with when it comes to this particular topic of thermochemistry, right? So if you consider, for example, honey in a jar, and the jar is closed, right? That would be a closed system, right? Because there's no exchange between what is inside the jar and what's outside. However, you can heat the jar, so energy can enter into the system, or you can cool it, which means that energy would be leaving the system. So therefore, we call this a closed system, all right? And that is basically what is shown here, right? So that's what happens in the case of a closed system. Now, in the case of an isolated system, in order to make this an isolated system, basically the container would have to be, what do you call it now? Insulated, all right? So a material like styrofoam, which basically will not allow for any heat exchange between the system and the surrounding, right? If this was entirely encased in styrofoam, then that would be an isolated system, because not only can you not have matter going in and out, but you also will not have energy going in and out, right? So that's the difference between a closed system and an isolated system. Okay, and here's a question being asked in this green box right here. Let me remove this. Okay. Question is asking, after the lid of the jar is unscrewed, which kind of system is it? And the answer would be an open system, right? Because if you unscrew it, then you can have the exchange of matter between the system and the surroundings, all right? So it's important that you understand the distinction between these systems. And more often than not, when it comes to experiments involving thermochemistry, we try to create the conditions of an isolated system, right? Because we want to look at what happens in a system without the influence of anything outside, so that we can, come to some meaningful conclusions. Okay, another term I need to introduce to you here is the concept of internal energy, which is the total energy contained within a system, all right? And that energy could be, well, very often is part kinetic and part potential, all right? So remember, kinetic energy is the energy an object has by virtue of its motion. And when it comes to molecular systems, there are three types of kinetic energy. You can have translational motion, where the molecule or the atom is moving along a straight line. You can have rotational motion, where if you're dealing with a molecule, the molecule will be rotating around a particular axis. And then you can have the third type, which is vibrational motion, where if you have two atoms connected by a bond, you can have this type of motion, all right? So collectively, these are called thermal energy. And the main reason why is because those motions are usually related to temperature changes. So we call collectively those types of energies thermal energies. And then we have the other part of internal energy, which is potential. And these are most often intermolecular and intramolecular forces of attraction as a result of attractive forces between atoms and as a result of bonds between atoms, right? And typically, we collectively call these energies chemical energy, because usually energy changes involve breaking and formation of bonds, and this takes place in a chemical reaction, all right? So when it comes to internal energy, there are two types. You have the kinetic part, which would be translational, rotational, and vibrational, and then you have the potential part, which would be basically as a result of forces of attraction between atoms and ions. Okay, so that's internal energy. Another term I need to introduce to you, which you may have met before in introductory chemistry, and that is heat. And there's a fancy definition of heat that you'll find in more advanced textbook, but for all purposes, we can consider heat to be the form of energy that occurs as a result of a temperature difference, right? So if you have two objects that are in contact with each other, right, one is hotter than the other, the energy flow will go from the hotter object to the cooler object. So that energy flow we call heat energy, all right? So as stated here, is the energy transfer between a system and its surroundings caused by a temperature difference, right? And this heat flow will continue until you end up with a situation where the temperature of the system and the surroundings reach the same temperature, right? And therefore, at that juncture, the heat transfer stops. So to explain this further, let's look at this hypothetical situation. So let's say you have a hypothetical thin wall which allows energy to pass through. And on this side of the wall, which represents the system, you have a collection of argon molecules. On this side of the wall, which represents the surrounding, you have nitrogen molecules, which would be the major component of the air that we breathe. About just under 80% of the air we breathe is nitrogen, right? So let's say that these molecules here are more energetic than the nitrogen molecules. So what will happen is that when these molecules bounce on the hypothetical wall, energy will transfer from the argon side to the nitrogen side. So therefore, that would be the heat energy that is transferred. Now, here's a very interesting question being asked down here in this box. It says, how do the root mean squared speeds of argon atoms and nitrogen atoms, molecules, compare at the point of thermal equilibrium, right? So at the point of thermal equilibrium, basically the energies are going to be the same because the heat flow will stop. So therefore, the amount of energy on this side and this side will be the same. And if you remember, we said, let me get out of this here. Oops, and get out of this. And let me bring this up. Remember, we said that the energy of a molecule is given by, the kinetic energy that is equal to half mv squared, all right? So we're gonna apply this to comparing neon to nitrogen. I'm sorry, argon to nitrogen. So if at equilibrium, or I should say specifically at thermal equilibrium, the average energy of the argon would be equal to the average energy of the nitrogen, right? So I'm going to write down an expression like this for each of these terms. So in the case of argon, it will be half mass of argon times the average velocity of the argon molecule or atom squared, and that would be equal to half the mass of nitrogen multiplied by the velocity of nitrogen squared. The halves will cancel out, all right? So what are we left with? We're left with this being equal to this, and if we look at the ratio established by the mass of the argon divided by the mass of the nitrogen, that would be equal to the velocity of the nitrogen squared divided by the velocity of the argon squared, all right? And if we're asked, let me go back to the PowerPoint. What did the, how does the root mean squared speed? So they're asking about the root mean squared speed. So basically, to find the ratio of the root mean squared speed for both nitrogen and argon, we do the square root of both sides. You're going to get, continuing up here, you're going to get Vn2 over VAR will be equal to the square root of the molar mass of argon divided by the molar mass of nitrogen. And then to find the actual ratio, we put the numbers in. So in the case of argon, the molar mass is 39.95, I think it is. 39.95 AMU. And the molar mass of the nitrogen is 2 times 14.01, which is 28.02. And basically that would give you, whatever that gives, that would give you the ratio of the velocity of the nitrogen molecules compared to the argon atoms at the same temperature during thermal equilibrium, all right? So that's basically how we would answer that question. Okay, any questions about this? Any questions? Any questions? All right, so let me go back to the PowerPoint and continue our introductory stuff. Okay, so the next concept we're going to talk about, we alluded to it earlier, work. As I said before, work is what is done when force is applied to an object and the object moves, right? The result of that is that energy would either be transferred to the object or energy would be lost by the object, in which case the object is doing work on the surroundings, right? So as stated here, work is an energy transfer, but the difference is, in the case of work, that energy transfer is as a result of force being applied to the object and the object moves. In the case of heat, the energy transfer is as a result of a temperature difference. So that's the difference between heat and work, all right? Heat is as a result of an energy transfer as a result of temperature difference, while work is as a result of force being applied to an object and the object is moving, right? Now, at this junction, this is very important. What you're going to see is that you need to, especially when it comes to answering certain questions, you need to pay attention to the sign of both work and energy mathematically, right? So very often what you're going to see is that when you're given a question, The question will not tell you directly whether or not work is negative or energy is negative, right? You have to basically figure out what it is in terms of the sign based on the information in the question and how the information is provided, all right? So let's talk about what the signs actually mean. If we're talking about a negative quantity of work, that means that the system is losing energy, which means basically that the system is doing work on the surroundings, all right? On the other hand, in the case of a system gaining positive energy as a result of work, what that means basically is that work is done on the system by the surroundings, right? So if the system is doing work on the surroundings, the system will lose energy. If work is done on the system by the surroundings, then the system will gain energy, all right? So it's very important that you understand the relationship between the signs and whether or not system is either losing or gaining energy as a result of either work being done on the system by the surroundings or vice versa. So it's very important that you understand is that there's no such thing really as negative energy or positive energy. Basically, the negative sign and the positive sign is a reflection of whether or not energy is lost or gained by the system, all right? Okay, so just to give you an example, again, this is a hypothetical situation. So here we have a situation where we have a gas trapped in this vessel, and we're going to assume several things. For example, we're going to assume that this plate here can move smoothly without any friction, right? And we have our gas here trapped. The initial volume here is V initial, right? And then let's say that the gas expands, right, to a larger volume, which is a V final right here, right? So basically what that means is that the system or the gas expanding in the system would mean that the system is doing work as it expands, right? So the formula for calculating the work would be this right here, all right? W is equal to minus P times delta V. Delta V would be the change in volume, right? And if you recall, in the previous chapter, no, wait a minute, no. Okay, I'm mixing up my topics. All right. So when it comes to changing anything, right, we always calculate change as the final value minus the initial value, right? So in this particular case, you'll notice that the final volume is larger than the initial volume, right? So therefore, the change in this case will be positive, right? Now you'll notice there's a negative sign right here, right? What that negative sign indicates is that the system is losing energy because the system is expanding against the surroundings. So the system is doing work on the surroundings, which means that the system is losing energy. And that's the reason why we say that the work done on the gas is negative P times delta V, all right? Okay, so this brings us now to a discussion of state functions. So this term state, I'm quite sure you learned about the states of matter, right? Solid, liquid, and gas, right? Well, it turns out that the term state is a bit broader than just that, okay? It does apply to that in terms of describing the different phases, but it's more than just that. It's basically its exact condition at a fixed instant. That's what we mean by a state of a system. And the state is determined by several things: the kinds and amounts of matter present, the structure of this matter at the molecular level, and the prevailing pressure and temperature. So based on that definition of a state, it does not necessarily limit to states of matter, solid, liquid, gas, right? You can have two different states, for example, in the same phase. So for example, let's say, let me get out of this here. Let's say you have, let me clear this. Let's say you have a piece of iron, and let's say the iron is a solid at, let's say, 50 degrees Celsius, right? And let's say all you did to this is heat it to 70 degrees Celsius, right? Believe it or not, those are two different states, simply because there's a temperature difference. That temperature difference would lead to energy changes within the system, the molecules in the case, or the atoms, I should say, in the case of iron at the higher temperature, will be vibrating more compared to at 50 degrees, right? So that's a change in state. Or let's say I gave you this H2 gas at a pressure of 1 atmosphere. And let's say that I increase the pressure to 3 atmospheres. Again, that's a change of state, right? It's the same gaseous phase, but the state is changed simply because there's a change in pressure, right? So the term state has a more broader meaning than just changing the phase of the substance. All right. So going back to the PowerPoint here, we talked about the states of matter. And another term that you need to be aware of is this term state function. And this is basically a property that is dependent, a quantitative property that is dependent on the current state of the system and not dependent on how the state was reached. In other words, the value of the state function is not dependent on the history of the system. All right, so that's a state function. And there are several state functions that we're going to meet in this chapter. Okay, and at this juncture, I want to introduce to you the first, or maybe reintroduce because you should have met this before, the first law of thermodynamics, which says, and you're going to see this worded in different ways in different textbooks, but it says here that it's in a physical or chemical change, energy can be exchanged between a system and its surroundings, but there are no energy change or no energy that will be destroyed or created, all right? So that's basically the first law of thermodynamics, also known as the law of conservation of energy. So simply put, what this law is saying is that in any physical or chemical change, energy will not be created nor destroyed, all right? That's basically, or another way of stating it is that the total energy of the universe is conserved or remains constant, all right? So that's basically the first law of thermodynamics, which will become important in certain problem-solving exercises, as you're going to see. So basically, as I said before, simply put, the first law of thermodynamics is saying that energy cannot be created or destroyed. And one conclusion we can come to is that when it comes to a system, the internal energy change in a system is simply the difference in energy between its final and initial state. So internal energy is one of those state functions, right? And the change in internal energy of a system depends only on the initial and final states, and it doesn't depend on the journey as it goes from one state to the next, all right? So simply put, we can represent the change in internal energy as the internal energy final minus the internal energy initial. And remember, whenever it comes to changing anything, as I said before, it's always final minus initial. The final value minus initial, all right? Another conclusion we can come to is that if energy changes occurs only as heat and or work, then this is the relationship between the change in internal energy and heat and work. So delta U, the change in internal energy, is equal to the change in the heat energy plus the work that is done on a system. All right? So that's the relationship between delta U, Q, and W. And again, it's very important that you understand the meaning of the signs associated with these terms, as you're going to see, I think, in the next slide. Exactly. So in the next slide, you need to remember how to interpret questions with respect to the signs of these quantities. So just to make sure that you understand how the signs related to what's happening here, if energy is entering a system, right, then basically the energy change for the system is positive, right? If energy is entering the system, then the energy change is positive. And that could mean one or both of two things. It could mean that heat is absorbed by the system. That would certainly increase the energy of the system. And then it could also mean that work is done on a system. So if heat is absorbed by the system and work is done on a system, then definitely the internal energy will increase. On the other hand, if energy is leaving the system, right, that means that the total change in energy is going to be negative. So what does that mean? That means that either heat is given off by the system, right, or work is done by the system. So in either case, the result will be that the change in the internal energy is going to be negative, all right? So again, very important for you to understand the relationship between the sign of the change and what is happening in terms of whether or not heat or work is going to be done on a system, or heat or work is going to be given off by the system. Okay, so to illustrate this, let's look at this simple question. It's a rather simple question, but again, this will illustrate the reason why you need to read the question carefully so you can interpret the signs that will be associated with these values. So the question says, let me just go through it first, and then I'm going to pick out the important parts. The question says, a gas does 135 joules of work while expanding, and at the same time, it absorbs 156 joules of heat. The question is, what is the change in internal energy? Now, remember, the formula for the change in internal energy is delta U is equal to Q plus W, right? Now, according to the question says a gas does 135 joules of work, right? So basically, if it does 135 joules of work, that means that work will be equal to minus 135 joules, right? Because the gas is doing 135 joules of work on the surroundings. Then the question says, and at the same time, it absorbs 156 joules of heat. So what does that mean? That means that heat, Q, would be positive 156 joules because it's absorbing heat, all right? So basically, we put these numbers into this equation. We're going to get 156 joules plus, and then that will be added to minus 136 joules. And then you do your number crunching. Okay, I guess I left my calculator upstairs. This looks like oh, this should be 135, my bad. So this looks like 21, yeah, 21 joules, all right? And that's it. So it's a simple example, but you have to pay attention. You have to look at how the question is worded so you can tell whether or not the different quantities are positive and negative, all right? Okay, any questions about this? Any questions? Any questions? All right, moving along. So now we're going to get into heats of reaction, and now we're going to just get into the connection between energy changes and reactions, right? So the heat of reaction is the amount of heat that is exchanged between a system, a reaction system, and its surroundings. And at this juncture, I want to basically talk about two different types of reactions when it comes to heats of reaction. We have what is known as an exothermic reaction, which is a reaction that produces heat. And in an isolated system, if you have a reaction in an isolated system, now remember, in the isolated system, you do not have any heat exchange between the system and surroundings, right? So basically, in an isolated system, if an exothermic reaction is taking place, then what will happen is that heat will be generated, and whatever is left inside of the reaction system will absorb the heat, and the temperature of that system will rise, all right? So that's what happens in an exothermic reaction. And the consequence of the system losing heat is that the system will go from from a higher to a lower energy, and the heat of the reaction is negative, right? So if it's producing heat, then the heat of reaction is negative. And then the opposite is true for an endothermic reaction. So in the case of an endothermic reaction, it will absorb heat from its surrounding. Now, in the case of an isolated system, the temperature will decrease, which is the opposite of what happens in the case of an exothermic system. And the system will go from a lower to a higher energy, which means that the heat of reaction will be positive. So just to mention a couple of examples of this, if you were to take a test tube and let's say you add, to use an example of an exothermic reaction, let's say you add a few granules of sodium hydroxide and it dissolves. If you were to feel the outside of that test tube, it's going to feel warm. And the reason why is that when the sodium hydroxide dissolves in water, it generates a lot of heat. In fact, depending on the amount of sodium hydroxide you add, the amount of heat generated can be very serious in terms of causing burns, right? So that's an example of an exothermic process. An example of an endothermic process would be if you were to take, instead of sodium hydroxide, if you were to use, let's say, potassium nitrate or ammonium nitrate, either one will do. If you add it to a test tube of water, it's going to feel cold, because what is happening in that case is that it's absorbing heat from the surroundings, so therefore it's absorbing heat from your hand if you touch it, and therefore it feels cold. So that's basically an example of an endothermic process. Okay, so let's look at these hypothetical. Well, the first one is definitely hypothetical. The other two are actually more realistic. So let's look at what happens in the case of an exothermic reaction. And if you understand what I'm about to discuss, then you should be able to predict what would happen in the case of an endothermic reaction. So let's look at this purely hypothetical situation. Highly unlikely to occur. We have the reaction taking place here in a vessel, and this vessel allows all the heat generated to leave, right? That is pretty much not going to occur, but let's say we can design something where that will happen, right? So what will happen is, oh, and by the way, the surrounding temperature is 25 degrees. It's constant at 25 degrees, all right? So what's going to happen is that all the heat generated will leave, and therefore the temperature will remain at 25 degrees, right? What is more likely to happen is this situation here, right? Where not all the heat will leave. Some of the heat will leave, right? The heat that is generated, but some will be absorbed by the contents left behind in the beaker. So what will happen is that the temperature of the contents would increase to above 25 degrees, right? To about 32.2 degrees in this particular case, right? So that is more likely to occur. And then if we're dealing with an isolated system, right? So remember, in an isolated system, any heat that is generated will not escape, right? So what's going to happen to the temperature, especially compared to this one? Well, in the case of this situation, the temperature will even be higher because none of the heat will leave, right? All the heat that is generated will be absorbed by what is left. So therefore, the temperature will go even higher, all right? So that's basically what happens in the case of an exothermic reaction in each of these different scenarios. And as I said before, if you understood what I just described, then I'm quite sure you're able to predict what would happen in the case of an endothermic reaction. So I'm going to leave you to think about that. If you have any questions about that, feel free to contact me about that, all right? All right. Now, what we're going to look at is what happens as far as internal energy changes occurring in a system under two conditions. One condition of a constant volume, and the other condition would be under constant pressure, right? So in the case of a constant volume, remember now, in the case of a constant volume, what that means is that there's no change in volume, which means that delta V is equal to 0. And if delta V, the change in volume, is equal to 0, that means that the work done would be 0. Because remember we said that work is equal to minus P delta V, right? So if delta V is equal to 0, work is equal to 0. That's what we're saying here. Now, if work is equal to 0, that means that because of this equation here, delta U will be equal to Q, right? And we put a little V here, QV, to indicate that we're talking about constant volume conditions, right? So basically, what happens, the way we would interpret this, is that all the thermal energy, let's say we're dealing with an exothermic process here, all the thermal energy that is produced from the chemical reaction will be produced as heat, and there'll be no PV work done, all right? So that's what happens under constant volume conditions. Now, constant volume conditions are very rare when it comes to chemical reactions. So most of what we're going to look at from now on will be situations where the processes will occur under constant pressure conditions, right? So we're assuming that the pressure is constant. So we're going to go back to this equation here. Let me rewrite it here. I prefer black ink. So let me do that. So the equation is delta U is equal to P plus D. I'm sorry. Delta U is equal to Q plus W, right? So what we're going to do now is replace W with minus P delta V, and we end up with this equation right here. And Q is basically QP, which is P means under constant pressure conditions. Now, if we rearrange this, we're going to get QP is equal to delta U plus P delta V, all right? And basically, the interpretation of this is that basically, whenever you have an energy change occurring, most of the energy will be released as heat, but some work will be done against the system. That's where the P delta V comes from, right? As a result. Again, we're assuming it's an exothermic process, all right? So this is what happens in most cases. In most chemical reactions, pretty much the conditions is more likely to be under constant pressure conditions as opposed to constant volume conditions, all right? So this brings us now to another term that I need to introduce to you, enthalpy. Enthalpy is, by definition, the sum of the internal energy and the pressure volume product of a system, right? H is equal to U plus PV. H is the enthalpy, which is basically the pressure, basically the heat change under constant pressure conditions. U is the internal energy, P is the pressure, V is the volume, right? So if you have a reaction occurring under constant pressure conditions, the QP, the heat change under constant pressure, is basically the change in enthalpy. And what is shown here is the example of a reaction that produces a gas. The gas is expanding against the surroundings, so therefore, this equation will certainly apply in terms of calculating the heat change based on the change in internal energy, the pressure, and the change in volume. All right? So this is just basically reiterating what I said before. Excuse me, most reactions occur at constant pressure. So for most reactions, the heat change of ours will be equal to the enthalpy change. Okay, so that's enthalpy. Very important that you understand some of the properties associated with enthalpy. Enthalpy is an extensive property. It depends on how much of the substance is present. So in other words, the greater the amount of substances involved in the reaction, the greater would be the enthalpy change. The internal energy, pressure, and volume are all state functions, which means that enthalpy is a state function as well. And enthalpy changes have unique values, which would have to be determined experimentally, all right? Enthalpy change also depends only on the final and initial state. So basically, it's the final value minus the initial value that gives you the delta H, or the change in enthalpy, all right? So those are just a list of some of the properties associated with enthalpies, which will become important when you're doing your calculation. So I just said a while ago that enthalpy changes are measured experimentally. If the enthalpy change is negative, that is an exothermic reaction. If the enthalpy change is positive, it's an endothermic reaction. And these diagrams here demonstrate that fact, or those facts. So in the case of an exothermic reaction, the enthalpy of the products would be less than that of the reactants. So remember, it's always enthalpy of the products minus the enthalpy of the reactants, which would mean that the enthalpy change is going to be negative, and therefore that's what happens in the case of an exothermic reaction. And then in the case of the endothermic reaction, the opposite is true. The enthalpy of the products will be greater than the enthalpy of the reactants, so therefore delta H would be positive, all right? Okay, what happens if the reaction reverses, right? In terms of the enthalpy change? Well, basically what will happen is that the sign will change, right? So if you're going from A to B and the enthalpy change is positive, then going from B to A, the enthalpy change would have the same magnitude, but negative, all right? That's going to be important too when it comes to doing certain calculations. So therefore, if you're going from A to B and then from B back to A, the total enthalpy change for all of that would be zero, right? Because they will cancel out each other. So just to give an example of this, let's look at this reaction, the reaction between liquid mercury and oxygen to form mercury 2 oxide. In this case here, we're going the reverse direction. So this is the reactant to form the products. The enthalpy change is 90.83 kilojoules. But if we're going the other direction, same magnitude, but the sign is opposite, right? And that is true universally, all right? So let's look at this example right here. Based on what we have learned, we should be able to do this example. The question gives you this equation here, right? And it gives you the enthalpy change for that reaction, right? And then it says, calculate delta H for this reaction, right? Now, my question to you is this. Compare this equation to this equation. What two things can you notice being the difference between them? There are two important differences between those two equations. two important differences. That's one, right? The second equation is the reverse of the other, of the first. In other words, the products in the first reaction would be the reactants in the second reaction and vice versa. So that's one important difference. What's the other difference? Exactly. So all the coefficients of the first equation are basically halved in the second equation. So the question now becomes, how do those two factors affect the delta H value, right? Now remember what we said. If you flip the equation, what happens to the delta H value? The sign changes, right? So the 52.96 becomes minus 52.96, right? Kilojoules, right? And then now, as he said, all the coefficients were halved. How does that affect the delta H value? Well, that means that this will be halved as well. Because remember, we said that the enthalpy would be an extensive property. And that's it. So once you calculate that, I don't have my calculator with me, so I need your help. Can somebody tell me what this gives? Okay, and that's it. So that's basically how you'd find the enthalpy change of this reaction here based on what was given initially. All right. Any questions about that? Any questions? Any questions? Okay, let's look at the second example. It says the complete combustion of liquid octane, and it gives you the formula, to produce gaseous carbon dioxide and liquid water at 25 degrees Celsius and at a constant pressure gives off 47.9 kilojoules of heat per gram of octane. Write a chemical equation to represent this information. Okay, let me explain what this is. I don't think this is actually 100% clear. Basically, what they're asking for you to do is, based on the information provided, write down something like this, including the delta H value. That's what they're asking for, all right? Now, what I'm going to do, since I'm going to need a space, whoops, I am going to copy this here and paste it onto this here. Let's see if this works. I try doing, I think it's going to work. No, it's not going to work. Or maybe I'm just doing something wrong. All right, tell you what, let me get out of this here and let me try Word. Okay, so that's a question. And let me do the okay. All right, so that's a question, right? So the first thing I would do is to what? What would be the first thing you would do in order to answer this question? Well, the formulas would be written, of course, yes, but I was actually looking for something else. You'd write a what? You'd write what? You'd write something based on the information that I'm circling right now. The equation. Right, okay, very good. So what would be the reactants based on what I circled? What would be the reactants? No, reactant. It says, okay, so C8H18, liquid state, plus what? Oxygen, which is always O2. And then the products will be carbon dioxide, gas, and liquid water, H2O liquid, all right? And then we would balance it. So how would you go about balancing this equation? Well, that sounds about right. Let me see here. So you have 16 carbons on both sides. You have 36 hydrogens on both sides, and you have 50 oxygens. So that's 32 plus 1850. Yep. So that's it, right? So you have to do that before you could do anything else, all right? Now, the next step is to find out the amount of heat change occurring. Now, again, here's where it's important for you to read the question carefully. The question says, at a constant pressure, gives off, right? Gives off 47.9 kilojoules of heat per gram of octane, right? Now, this equation is telling you what happens for 2 moles of octane, right? So this is how I would set this up. I would say 2 moles of C8H18. I would convert that to grams, all right? So here I'm going to put 1 mole of C8H18, and then I need to calculate the molar mass. Okay, you know what? I'm going to cheat. I don't know if I showed this before, but there is a website. All you have to do to get to it is type in molecular molar mass calculator. And then you enter the formula in the space. Oh, no, you click on that first. And then you enter the formula. So C8H18 is the formula, calculate, and then it gives you the molar mass here, right? I've used this over and over again. It has never made a mistake, even though they put a, what do you call it, a statement saying, you know, they can't guarantee it, but works every time. Okay, so let me go back to, where am I? The word. Okay. So, wait, what did I say it was? 114 point what? 23, okay. Grams of octane, C8H18, right? And then now, I would multiply this by this right here, because this says for every 1 gram of octane, the amount of heat that is given off is 47.9 kilojoules. But because it says given off, I would have to put a minus sign right there. So minus 47.9 kilojoules over 1 mole, over 1 gram, I'm sorry, of C8H18. And then you work this out. So again, I'm going to need your help to do this part. And round off your answer to 3 sig figs. So what's the answer? Repeat that. 10,900. Okay, that sounds about right. And that would be kilojoules, right? Okay. And that's because this cancels with that cancels with that. So you're going to left with kilojoules. So therefore, delta H here, oh, and don't forget the negative sign. So delta H here would be equal to minus 1,900 kilojoules. And that's how you do that. All right. Okay, any questions about this particular example? Any questions? All righty, now I'm going back to the PowerPoint. Let's see what's next. Maybe I should get you started on assignment number 6. All right, let me get you started on the first 2 questions on assignment number 6. Just questions numbers 1 and 2. I'll be right back. Oh, by the way, the delta E is the same thing as delta U. I'm sorry. In question number one, in some textbooks, you see delta E. It's the same thing. Yeah. So, yeah. Sorry about that. Sorry about that. Yeah, that's how things kind of vary from textbook to textbook. Okay, are we finished with those questions? Any questions about any of these?
No idea.
Oh, number 2 is using, hold on, let me bring back up this here on the screen. Okay, so number 2, it says calculate the kinetic energy in joules, calories, and kilojoules for a particle. It gives a mass and it gives the velocity. So the equation we're using is this. Kinetic energy is equal to half mv squared. So in the case of the joule calculation, it's half times the mass of the particle in kilograms. Now they gave the mass of the particle in grams. So you have to convert that to kilograms by this here. And then you multiply by the velocity, which is given in meters per second. So that's 6.00 times 10 to the 5 meters per second. And then you square all of that. And that's it. And then now, once you get the value here, this value is going to be in joules. Once you get the value in joules for the calories, you would have to multiply that value by 1 calorie is equal to 4.18 joules. And that's it. And then to convert to kilojoules, you just multiply by 1 kilojoule over 1,000 joules. And that's it. All right. Okay. Let me go back to the PowerPoint here. Now, I think it's going to be the last thing we're going to talk about today. And this has to do with looking at the relationship between the mole ratios and the amount of heat change in any chemical reaction, right? In other words, we look at the relationship between the stoichiometry of the equation and the value of delta H, right? So if you're given, oh, I skipped a slide. Oh, okay. So if you're given a problem where you're told that the reaction is exothermic, what you can do for the purposes of solving the particular problem is that you can treat the heat change as a product because it is produced, right? So just like any other products, that would have been produced in a reaction, you can treat the heat change like that. If the reaction is endothermic, then you treat the amount of heat as a reactant because, of course, in an endothermic reaction, the heat is used up, right? Another thing you can do, as stated here, is that you can generate conversion factors which relates the heat change to the coefficients of the different substances in a balanced equation. So, for example, let's say you're given this equation here and you're given the delta H for that reaction, right? Then we can establish relationships between this value and the coefficients for each of the substances. So, for example, you could write minus 184.6 kilojoules per mole of hydrogen because you have 1 mole of hydrogen represented here. Same thing for the chlorine. And you can also have the relationship between the same amount, but you have 2 moles of hydrogen chloride because of the 2 here, right? And of course, you can use the flipped version of each of these, depending on the kind of problems that you're trying to solve. All right. So an example of this is right here. They gave you this equation. They gave you the delta H value for that reaction. And the question is saying, what is the enthalpy change associated with the formation of 5.6 moles, 5.67 moles of HCl here in this reaction, right? So what I would do is start off with, I'm going to do it up here, 5.67 moles of HCl. And then the conversion factor that we use here is that I'm going to put 2 moles of HCl down here. And up here, I'm going to put minus 184.6 kilojoules. And then you do that. Again, I need your help. Can somebody work this out? And round off your answer to 3 sig figs. 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 3 I'm sorry? Minus 523 kilojoules. Yeah, that looks right. Okay, and that's it, all right? So that's how you can relate the mole value to the amount of heat change occurring in the reaction. Okay, I think this is going to be the very last thing we're going to talk about. Calorimetry. Calorimetry is basically how we measure heat flow, and a calorimeter is a device used to making this measurement, and they come in different levels of sophistication. I would call this the ultimate in low-tech apparatus for this particular measurement, consisting of two styrofoam cups, a stopper here, which has two holes, one hole for you to insert the thermometer in, the other hole for you to insert a stirrer, right? To make sure that whatever is inside there is mixed, right? Styrofoam, of course, is the material of choice when it comes to this setup because styrofoam is highly insulating, so it doesn't allow any heat to escape or enter into the system. So this would be considered to be an isolated system, right? Now, for organic reactions, or for reactions of organic compounds and combustion, a more sophisticated setup is used. We call this a bomb calorimeter because basically what you're doing is burning whatever the organic compound here is. So here's your organic compounds. You have two leads, which leads to an external circuit. You have the steel bomb right here, which allows heat to pass through it. So when the reaction takes place, produces heat energy, the heat enters the water, you measure the temperature change of the water. You have a stirrer here, which allows the heat to be uniformly distributed in the water. And then based on the temperature change and other factors, which we'll talk about later on, you can actually determine the amount of heat that is produced in this reaction. So that's just another form of the calorimeter, which is a bit more sophisticated than the simple one that you see here. Okay, so when it comes to calorimetry, basically the heat that is produced in a reaction is absorbed by the calorimeter and is constant. So basically we can write down that Q of the reaction would be equal to minus Q of the calorimeter, all right? Because the heat that is generated, for example, if it's an exothermic process, the heat that is generated by the reaction will be absorbed by the calorimeter. So that's a relationship between the heat of the reaction and the heat change of the calorimeter. In the calorimeter, we measure the temperature change in the water to determine the heat absorbed or evolved in the reaction. So basically, delta T, the change in temperature, is what we need. Now, here we're going to get into how do we make these calculations. Some terms have to be defined here. The first of which is heat capacity of a system, which is the amount of heat required to change the temperature of a system by either 1 degree or 1 Kelvin. And please note, it doesn't matter if it's measured in degrees Celsius or Kelvin, the numerical value will remain the same. So C, I think I have an equation here. Yes, there's the equation. C, the heat capacity is equal to Q, which is the heat change, divided by the change in temperature, right? In this case, the units would be in joules per degree Celsius, or it could be joules per Kelvin. Again, it doesn't matter if it's degrees Celsius or Kelvin being used to measure the temperature change, right? So that's the heat capacity. And then we have what is called the molar heat capacity, which is the heat capacity of 1 mole of a substance. To be perfectly honest, I don't anticipate us using this term in any future calculations. What you will definitely be using is this, the specific heat, right? And please know that the symbol for specific heat is the lowercase c, while this the symbol for heat capacity is uppercase C. So the specific heat is the heat capacity of 1 gram of a pure substance or homogeneous mixture. And the equation relating lowercase c to uppercase C is right here. The specific heat, lowercase c, is equal to the heat capacity, uppercase C, divided by the mass. And if we replace uppercase C with Q over delta T, we're going to get this equation here, right? So this equation is what you can use to calculate the specific heat. And the specific heat is actually more useful for pure substances compared to heat capacity. It is actually used as one of those physical identifiers, right? Just like density, melting points, and so on. A more common way of expressing this equation is this right here. Q, which is the heat change of the reaction, is equal to C times M times delta T, right? And Q is in joules. M is in grams, usually. And delta T would be either degrees Celsius or Kelvin, which means that the units of C is either joules per gram degree Celsius or joules per Kelvin. I'm sorry, joules per gram Kelvin. All right? So again, it doesn't matter if you use this or this. For specific heat, the numerical value will still be the same. All right? So that's specific heat. So just to give a quick example here, question is asking, calculate the heat capacity. Basically, they're asking for the specific heat. Oh, no. They're asking for the heat capacity, I'm sorry, which is uppercase C, of an aluminum block. It gives the heat, which is Q, and it gives you the initial and final temperature, right? So C is going to be equal to Q divided by delta T. So Q is, now again, you have to pay attention to how it's worded. It says absorbed, which means that Q is positive. So this is going to be positive 629 joules divided by delta T, which is always final minus initial. The final is 145 degrees Celsius, and the initial is 22 degrees Celsius. And that's the setup. So again, I'm going to need your help. What does this give? The 3 sig figs. .11 and joule, exactly, joules per degree Celsius. Okay. And that's how that is done. All right, we're going to stop here for today and continue this discussion next class, Thursday. All right.